If we could go back and start the next session, please.
Yeah, we're both presenting. Okay. All right. But you still keep to 15 minutes, huh? Yes. 16. Let's say 16. Okay. Thank you.
So our next session will be on supply and demand for critical minerals. And the session will be chaired by Rabah Arezki. So we're just going to take a few minutes to let everyone settle in. And then we can start.
Thank you very much. And we're going to get straight to it. So we have a great panel with lots of charts, lots of perspective from the sky, including. So we will start with Rod, who is at the School of Mine, and I have asked him to tell us a little bit about the School of Mine before he starts his presentation. So you can deduct that from your 15 minutes. All right? You want this?
I hope I'm able to meet expectations for the applause. Anyway, thank you very much to the organizers for inviting me to participate. I am Rod Eggert. I am from the Colorado School of Mines. The Colorado School of Mines is one of the few universities worldwide that I think covers mineral resources and the materials derived from them in a soup to nuts fashion, beginning with basic geoscience, through mining engineering, metallurgy, material science, environmental science and engineering, geophysics, and then the program that I am affiliated with, mineral and energy economics. So we are very much involved in mineral resources generally and processing, and then in this relatively new phenomenon, critical minerals and materials, which we saw from the first session, kind of blur together to some degree, and the cynic in me would say that really all minerals are critical to someone for something. What is critical depends on who you are, where you are, and when you ask. And to some degree, as a result, the distinction between minerals and critical minerals is a bit, it's not helpful almost, but it has, I would say, the word critical captures the attention of policymakers who are distracted because they have to be familiar with everything, which means they really can't be in-depth knowledgeable about everything. Anyway, with that, I'm happy to be here, happy to talk with you informally about anything that I've said already or will say in the coming few minutes. And with that, if I can have my slides, please.
Good morning. Your PowerPoint is going to be on the screen, okay?
Very good. Well, thank you very much. Let me first of all acknowledge my co-author, Ilenia Romani, who is from MIT University. I should have included the MIT logo here, but I've simply included the two logos representing the two hats that I wear. I'm an economist in the Department of Economics and Business at Colorado School of Mines. But also for the last 13 years, I've been deputy director of something called the Critical Materials Innovation Hub, which is a research consortium of universities, national laboratories, and companies focusing on technological innovation for selected energy materials, and we are funded by the U.S. Department of Energy. So we've been in the critical minerals and materials game since before it became so prominent in public discussions. And I hope that results in my being able to say something useful. Usually, because I'm an economist, talking to scientists and engineers, I'm talking about the importance of not overlooking economic behavior, prices and costs, and how government policies influence prices and costs, to scientists and engineers who work in the world of stocks, physical stocks and flows. Well, today I'm turning the tables a little bit and talking largely, I think, to non-scientists and engineers, and in particular economists, and what I've learned from my science and engineering colleagues that are useful, I think, in understanding critical minerals and materials. And I've summarized these into 7 lessons. I'm going to spend most of my time, or much of my time, on lesson 1, and then go through more quickly lessons 2 through 7, which are developed more fully in the paper. So lesson number 1, cumulative availability curves provide insight into future supplies. Often as economists, we use somewhat stylized upward sloping supply curves and rely and think and are biased towards thinking that the market will solve problem and price signals will solve issues related to supply. But by looking at cost engineering estimates or engineering costs, one can gain some more specific insights into future supplies, and more specifically about where, when, and at what cost future supplies may emerge. So what is a cumulative availability curve? Well, here is one cumulative availability curve in the case of lithium. What are on the axes? The vertical axis is unit costs, production costs per unit of lithium production, denominated in dollars per ton of lithium carbonate equivalent. Be careful with the horizontal axis. It looks like it should be a production or supply rate. It's not. It's not a supply curve. Rather, it's production or resource that is available over all time. So it's a plot of resources, some of which are in production today, but most of which are simply potential sources of supply in the future, ranked from least cost to high cost. A couple of things to note in terms of reference points. Current annual production, if you think of that as a vertical line, is virtually indistinguishable from the vertical axis. So current production annually is very small relative to known resources, and that's what is represented on the horizontal axis. Known resources in the sense that these are resources that have been identified and examined in sufficient detail such that we imagine they might be technologically and commercially viable at some point in the future. And then reserves, the current working inventories at mines and other production facilities, are a subset then of these resources. And so what do we note about when, where, when, and at what cost? Well, obviously, as we move from left to right on this diagram, we go from low cost to high cost resources. These are estimates. Notice the 2 different colors. I'm not sure what color that is. It's kind of yellow and red. Let's call them yellow and red. The yellow resources are brines. So these are brines especially in the Salar de Atacama in Chile, Argentinian brines, brines in Bolivia, that are known to exist with some degree of confidence in a physical sense and might someday be commercially viable. The red columns or red bars represent hard rock resources typical of the current production in Australia. And so this gives us some idea, if we look at the information behind these columns about where future production might occur, with what technologies, and when, in the sense of some of these are exploration projects. It will take longer to bring them into production if, in fact, they ultimately do come into production. Others are in production and therefore have a higher degree of certainty about their viability. Notice also the smaller gray columns on the right-hand side of the diagram. These are what we, and I was part of the team that put together this cumulative availability curve, what we have labeled unconventional resources, meaning resources that have not up until now been commercially and technically viable to produce. These include things like the brine resources, the geothermal brines that a previous speaker talked about today, which are lurking in the background and undoubtedly are much greater in quantity than what are represented here. These are simply unconventional resources for which there are good quantity and at least approximate costs. Much of the brine resource isn't even in this diagram because we didn't know enough about the quantities and costs to feel comfortable including these in the diagram. A little more about the cumulative availability curve. Known conventional resources have more than doubled since 2009. The figure I showed on the previous diagram is in the background, yellow and red colors. The lightish zone represents a cumulative availability curve constructed and published in 2008 or 2009. So our knowledge about lithium resources has increased significantly. And as well, the estimated costs have increased just over the last 15 years. So even though from one year to the next supply is pretty inflexible, given a decade or two, supplies can be quite flexible. The location of conventional resources and production differ. The blue columns represent current or mine production or resource production in the case of brines in 2022, and the orangish or reddish are the conventional resources in the same year. And you can see Australia represents, or Australian mines represent, about half of world mine production at present, but the geographic distribution of just known resources is quite broader. I talked about unconventional resources, which could be disruptive. And the first two columns, what we have on the vertical axis are our estimates of million metric tons by unconventional resource, and there are many. But the first two, geothermal brines and oil field brines, are two of the examples highlighted by John Blundy earlier today. Okay, so that was lesson one. Relatively more quickly, or absolutely more quickly for the remaining lessons. Number two, geologic deposit type, ore grade and metal co-occurrence, influence extraction feasibility, costs, and production and processing. I probably should have said, and investment decisions. Brine deposits for lithium, for example, and hard rock deposits have much different characteristics and require different processing. Ore grade. Ore grades have generally fallen over the last several decades and certainly over the last century, and I'll talk more about them later. And then especially important when we think about how nature influences economics, metal co-occurrence. And just a couple more examples building upon what we heard about earlier this morning. And here's a wheel. Hope you can see it in the back. In the middle, in blue, we have the host minerals or the major metals. So it's things like aluminum and copper, nickel, zinc, and lead, which drive the investment and operating decisions at mines. And then arrayed from the center outward are other elements produced in association with the major metals. And a couple of examples. So if I look at copper as the major principal metal, we also have things like silver, Ag, and gold, Au, produced, noted in the light bar, which represent significant byproducts of copper operations, but for which there are also significant own production facilities. There are silver mines, there are gold mines. If we move out to the white zone, these are elements for which essentially all of the world's production comes as a byproduct either of copper or of one of the other materials. If we look at aluminum in the upper part of the diagram, almost all the world's gallium today is produced as a really, really, really minor byproduct of the aluminum production process. And so joint production is a key aspect when thinking about the economics of production. Lesson 3, new processing methods likely will continue to enable economic production from lower grade ores and more difficult to separate elements. As I noted a moment ago, ore grades have declined significantly for almost all types of mineral resources over the last century. And yet, in many cases, costs have stayed the same or fallen, and that's because of the cost-reducing impacts of improvements in exploration, mining, and processing. And often lower costs lead to downward pressure on prices, and we are likely to continue to see this happen in the future. Number 4, demand for critical minerals cannot be modeled by extrapolating past trends alone. We often, as economists, think about using some sort of time series econometrics to extrapolate from the past. And yet for many of the minor metals, which make up the majority of those things designated as critical, new uses or lost uses that can happen very quickly are key characteristics. And so it's helpful to use bottom-up estimates of material requirements to help explicitly incorporate potentially disruptive technical change into estimates of demand or at least potential material requirements in the future. We think about different magnet compositions, non-rare earth magnet compositions, which could be disruptive. And there was an article in the New York Times a couple of days ago about this topic. Or batteries. What if sodium ion captures some of the market for lithium ion? What if nickel replaces cobalt in battery anodes even more than it has at the moment? All of these are disruptive and are unlikely to be picked up by kind of mindless or extrapolation of past trends. Number 5, substitution is multifaceted and typically not simply one material for another in existing application. Rarely does it happen that one material is simply plucked out of an existing system and a new material plugged in. Rather, substitution, which we often in economic models think about being driven kind of mechanistically by changes in relative prices, often requires re-engineering, which takes time. And so if we think about the use of lithium-ion batteries as a substitute for nickel metal hydride batteries in hybrid vehicles. This took time in re-engineering because different battery types require different quantities of batteries to achieve similar properties. Number 6, most critical minerals are not homogeneous commodities, and they're not commodities in the sense that a commodity is a standardized product traded in, such as refined copper, but rather if we think about rare earths and lithium, for example, these are really specialty chemical industries where hard rock lithium concentrate has a somewhat different, although partially overlapping set of uses with lithium carbonate, which in turn has somewhat different uses than lithium hydroxide. We have high sodium and low sodium lithium metal, each of which have different prices, which need to be considered in our economic models. And finally, number 7, scientists and engineers are often skeptical of monetizing life cycle impacts. We as economists want to monetize the value of a human life or lost work or scenic vistas. Well, I would say most of the scientists and engineers, when I start talking about that, look at me cross-eyed. They get a blank look in their face and are much more comfortable with a multi-attribute world of decision-making, more from the world of decision science than they are with economic monetization. Well, I think I'm at risk of exceeding my time, and so with that, I will stop. Here are the 7 lessons in one slide. I actually can't remember 7 things. I should have boiled it down to 3 or 4, but I'm sorry. Thank you very much.
Thank you. So we have time for a few questions. I can't help but ask you about John Blundy's proposal on using this geothermal source of energy. But I also noticed that you haven't emphasized the importance of energy in the process of transforming this rock or extracting the ore from these rocks.
Energy is very important for sure, and perhaps I should have included that. We should have included that in the paper. There's actually other work that I did with a graduate student that suggests, really confirms the Sherwood plot finding that it's not so much average crustal abundance that influences price, it's the energy requirements in production that influence price. So you can have less abundant elements on average, have lower prices because they require less energy to process.
Anything on John Blundy's proposal?
No, I think I would include that in the category of unconventional resource, and so I think we should investigate that further. I would also add, as another often unconventional resource, recovery of critical elements from the byproducts of ongoing operations, but also from historical wastes.
If there's any question,
I have a follow-up question on energy. So very often I hear that engineers are very concerned on how much energy do you need to extract a material that you need to produce energy, and that sometimes, I mean, this is not adding up in the sense that you need more energy to extract that material compared to the energy that you will be able to generate with this material. I mean, I just would like to have your thoughts about that.
I don't have deep expertise on that particular topic, but I have a response similar to many economists, and that is the form of the energy is also important, not just the quantity of the energy in terms of the decision about the use of energy.
If you could just clarify the last, because I think you were a little bit rushed, why is it relevant that economists or engineers that value life differently? How does that affect learning about mining?
Where I was coming from with that point has to do with life cycle assessment and material flow analyses. That in my experience, scientists and engineers in the world of industrial ecology, in particular, are more comfortable with quantifying the life cycle impacts of the production and use of a material through a set of 9 or 10 or 11 categories. Impact on human health, carcinogenic, non-carcinogenic, impact on carbon emissions, impact on aquatic life, land use, other environmental inputs and outputs, each of which is denominated with a different unit of account, and are more comfortable simply acknowledging that there are different units of account, and I would say are more comfortable with their abilities to intuitively weight them than they are with a more formal method of monetizing the life cycle impacts of resource production and use.
Thanks for your talk. In a review of the 7 important issues or warning flags for us, I was trying to imagine what is the specificity of critical raw materials or minerals as compared to fossil fuels across these 7 points. Do you have a view where is there really a difference for us? Maybe 0.4 on the forecasting the evolution of demand, or maybe some other points?
I think there are many similarities between critical minerals and energy. I would say there are even more similarities between critical minerals and mineral resources. I could have given the same topics, I think, if the focus of the meeting this week was the scramble for minerals as opposed to the scramble for critical minerals. But I think between energy and minerals, it's quite similar.
Wonderful, thank you. Thank you. So I'm going to invite Per Magnus. So Per Magnus is a senior advisor at Rystad, and I'm going to also ask him to quickly introduce Rystad. Maybe tell us a little bit about.
Yeah, thank you, Rabah, and thank you for the invitation, and thank you for the presentation I just heard. It was so many lessons learned from your very wise presentation. Well, my name is Per Magnus Nysveen. I'm coming from Rystad Energy. Rystad Energy is a commercial organization, so we make money on research. We are 900 people. We have 40 offices around the world. My department, the research department, has 400 people. And we do research related to, for instance, battery markets in China. We have a large team there in China. We do some minerals, some mining research in Australia. And we are covering all energy markets with a large office in Houston, large office in Singapore. And I'm from Oslo. Our headquarters is in Oslo. How many has heard about Rystad Energy before today? Yeah, that is very good. Thank you. Okay, so I have many slides, and there is many figures and many numbers. So I would enjoy seeing you taking notes and keeping your numbers. That's one way you can remember me. Pictures, it is okay to take pictures, but I prefer that you note the key numbers. It doesn't switch.
You really don't want us to take pictures.
Yeah, but you got it to work, right? Yeah. So how long time do I have? 15? Oi. Okay. I will rush through this. So I will talk about the energy systems and various transition scenarios. Of course, talk about battery metals, which is used for electric transport and stationary storage, and permanent magnets and rare earth. I think that many of you knows more about the particularities here, but I will relate it to the energy transition. First of all, when you do outlook within the energy world, you really have to look at everything in context. Everything ties together, and that is more and more true. For instance, oil demand, it all depends on electrification of transport. And here you see from the left side the primary energy sources, electrons on the top, molecules on the bottom, and on the right side you have all the consumption parts. And of course, one advantage with electrons as compared to molecules is that they are consumed in the same instant as they are produced. And there is no need for storage and material transports. But minerals, molecules, they are needed to enable that transition to electrons, as you know. So now looking at the energy transition that we are in now, we have had past transitions that has gone quite fast. Some transitions has been extremely fast. For instance, from coal for transport, for train transport to diesel happened within a decade in the US. But you see that we have all had the transition from bio to coal, from coal to oil, and now we are having a quite quick transition from oil to new technologies and new energies and renewables. This is just one fantastic example of how far we have come on solar power. So this is one of the largest installed solar farms in the world. It covers 20 square kilometers. It can power at the peak 2 gigawatt, 2 billion watts. And the generation cost is very low. The life cycle cost, $13 per megawatt hour. And to put that in context, you can drive 500 kilometers with an electric car for only $1.3 with the cost of that solar farm. And these 2 gigawatts can be compared with the global installments in 2025, which is 600 gigawatts. So this year we are installing 300 equivalents of this huge farm in the world. And now looking at the energy forecast and the energy mix for the next 25 years and looking at the history, you see that half of all the primary energy in the world goes to losses. And we talked about power for minerals and materials and metals. That is this black line here, actually. So in the general context, it is a visible, very visible consumer of energy in the minerals and metals processing. For instance, steel emits more carbon dioxide emissions than all the passenger cars in the world. So it matters even more on emissions than on energy consumption. But that is steel. But you see that the primary energy demand will go down after 2030, even though the useful energy will increase clearly going forward. Now, looking at data centers, everybody is talking about data center, and you see this yellow is the power demand, the global power demand for data center, and it's going to triple over the next 10 years. And to compare, I've compared that with all power that goes into electrifying road transport. And you see that already today, this is more than Germany. This 500 or 600 terawatt hour used for data center globally is more than Germany. And to compare with where we are going to get in 2035, this corresponds to 3,000 terawatt hour power consumed in the EU. So it's a tremendous source of power, the data centers. Now looking at the global power demand and the mix going forward, you see that the renewables is the upper wedges. and that is solar is growing tremendously. This 600 gigawatt that was installed in 2025, if you continue for 10 years with that same pace, you will be able to replace all the oil that goes into road transport, 50 million barrels, by electricity. If you continue for 10 years installing so much solar power. So this is going very fast. It's the cheapest source of new energy without any doubt, but it has the intermittency, of course. And then onshore wind, offshore wind. Offshore wind is growing fast, but it's starting from a low side. And nuclear is growing by something like 50% in this time frame. So that is also coming strongly to provide a steady zero carbon power source. Looking a little more at data center and nuclear. So there is a kind of marriage between data centers and nuclear power. But all these are plans, so this date is announcement plans. But there are some tremendous large projects here with small modular reactors, 12 gigawatt power into data centers. But this project is something that is not really planned to be realized before in the 2040s. So nuclear is really long term. But there are really serious plans by the technology companies to secure power from large and small nuclear plants and also geothermal. But on top of this, there is a lot of projects that combines solar, wind, and gas peakers for data centers. That provides also an autonomous, safe source of energy by using very little gas, but the combination of solar and wind is very important because they are synergic. You have more wind when you have less sun. So then you need less gas from the gas peakers. Now looking at nuclear a little, historically there has been tremendous overruns of costs and development time. So you see historically, so now the average development time has been 7 years from you start construction till you can start generate power. Average is 7 years. North America has been 8 years. The Chinese has managed to do this quite on time. The average plan time is 5 years. In reality, it takes 7 years, and in North America, it has taken long term. But we also see a lot of overruns there. So I am a little kind of doubtful about all these projects that are planned. I don't think many of them will maybe be realized. And SMRs, it has to be proven. It is not proven yet. The scale that is needed to make SMRs economic will take time to be achieved. Now, looking at what we are saying about the entire emissions from energy going forward, and comparing that with various scenarios, we think that it will hardly be possible to emit more than causing warming of 2.2 degrees, because the resources to get to very high emission scenarios will just be too costful, and because of demand elasticity, you will not see scenarios that can have much higher warming than 2.2 degrees. Good news. But otherwise, it's very expensive and hard to get further down than 1.8, 1.9. So we think that the global warming will be something below 2 degrees. That the emission that comes out from our most likely energy mix scenarios going forward. By the way, the budget for 1.5 is now 0 degree with 0 gigaton CO2 with some confidence. So we have achieved more or less 1.5 as we talk. And now, of course, the electrification of transport is extremely important because of the energy loss that you have from a conventional car. There is almost no energy loss from an electric car. And also the maintenance cost is 1/3 of the maintenance cost of a conventional engine, because it has hundreds of parts, while in an electric engine, it's only one part that moves, more or less. Now looking at where we are on electric cars. So this is very fresh data up to September. And you see that globally, we have almost achieved 35% of all cars are now electric. And it has been grown by 5 percentage points every year up to now. But now China is maturing, so it will not grow as fast going forward. I think I will just, I have to pass some slides here, but this is a forecasted sales of passenger vehicles. We think that in 10 years from now, half of all the cars sold in the world will be electric. When it comes to the demand for batteries, then the chemistry is very important, and the LFP, the nickel-based chemistry, the nickel-based chemistry is dying. It will peak and then fall. And the winning chemistry is the LFP chemistry, the orange. And then there will be some new chemistry, solid state, sodium ion, and there will be also some recycling going forward. And the metals composition, you know it probably very well, but going forward, they will be used for less nickel, almost no cobalt, not much manganese, but lithium will still be needed in the new chemistry. And the share of metal cost in batteries is 30% for nickel-based and only 10% for LFP batteries. Yeah, I would drop this, but we see from the past that the mining business within energy metals has been very responsive to prices. So they increased supply very significantly, 23, 24, as a response to this shortage we got and the high prices. And that tells a little about the elasticity in the sector. We are able to respond to bottlenecks. Now, copper, so that is one of the, I would say, the metals, energy metals, where we really see that cost will increase in the future because extraction goes deeper and deeper. So this is from Australia, from BHP. You see that with that almost doubling of the global copper demand in the very long term, we will see copper prices increasing robustly and steadily going forward. And copper is a large part of the overall cost in the new energy systems, of course. And now, looking at the overall demand going forward for the battery metals, we think that it will peak out in 2040, and then there will be quite a lot of recycling in the long term. Electric vehicle batteries can be used for storage and so on. Here we just compare with the energy is a small part of the overall market for nickel and manganese, as you know. That makes it less critical from the view of prices for the energy sector. I think that many of you knows all the other uses. The other uses of all the energy metals is very important. So all the yellow is other uses. And you see that lithium is, most of the usage for lithium is coming from electric vehicles. About half of the demand as of today is from electric vehicles. Yeah, and then how large part of the minerals will come from the energy sector will increase very much. For lithium, today 60, and it will become 90%. And other magnet rare earth, the share of magnet rare earth in energy system will double from 20 to 40% over the next 25 years. Lithium capacity can triple, and what is really coming in the United States is direct lithium extraction going out, but there is risks related to this capacity. So I think in reality we are maybe talking about economic capacity, risk capacity, that will at least double in the next 5 years. But the potential with all the plans out there is to triple over the next 10 years. When it comes to wind, where you have large part of permanent magnet demand comes from wind turbines. Going forward, and now right now there has been a cost jump on turbines, so actually the demand or the installments is falling in the next 2-3 years, and then we will have a steady growth, and offshore will grow. The largest offshore turbines are now 20 megawatts, and the permanent magnets, they can weigh up to 10 tons. Okay, I think that I'm 1/3 in the slides, but yeah, we can, that's life.
I think it was abundantly clear that you're doing a great job, both on the oil front. You didn't talk about your work on the bottom-up approach to oil, but Rystad has an incredible amount of work on pinning down all the global map on oil and gas. But it looks like you're also doing that for mining. If there's any question, yes, please. Yeah. Yeah. So, yeah.
So we all love you because we love your data, but except some of us are poorer than others, so they are also pricey. But can you tell us something a bit more about your data, particularly the use of that for researchers as far as it goes for critical mining? Because we know, at least I know your stuff for oil and gas stuff and all that stuff, but could you say a bit more on how advanced that is nowadays? Are you covering all the mines, or is it covering part, all that stuff?
We cover the swing mines, the critical mines, the large mines and the large companies. We are following the companies. Investors are very interested in minerals, so we do corporate research on the large public mining companies. Otherwise, we are doing very detailed research on the costs of batteries, how that can develop. And that is why we really need to follow the minerals refining markets. And we are also doing research on what's the cost of diversifying the supplies from China to other countries. And we are working with governments on that side. But we work with investors, we work with mining companies for the reports and the benchmarking, and we work with governments on geopolitics related to minerals.
I'm interested in your views on the Trump shock. Can you tell us what ways you think it's been most consequential, how large the effect is? Are there other minerals, other markets where it's not really having much effect?
Yeah, first of all, it has very little effect on the U.S. oil production because that is decided by corporations. But now we do research. I'm not an expert on the geopolitics on minerals, but from the preparation to today, to me it is very obvious that the resource side on critical minerals is not so critical. It boils down to really the geopolitics and the concentration. That is what makes it critical. The cost of extracting and the change of technologies just makes that the technical side doesn't seem to be a risk for the energy markets. So it boils down to geopolitics and the cost of diversifying.
Thank you for the presentation. My name is Mete and I'm part of the Oxford Rystad research group as well with John and Rick. And as part of our research, we're looking at the co-recovery of minerals and energy from geothermal resources. And in that sense, what you said about geothermal energy use for the data centers was quite interesting to me, because one of the main challenges that we encounter in the development of geothermal is some rich regions like Eastern Caribbean nations. They have huge potential when it comes to geothermal energy, but they don't have much demand of electricity, and that's why many developers are not much interested in investing in these regions. And one of the solutions that they come up with this is to establish high energy intensive sectors there, like data centers. I was wondering, how likely do you see the establishment of data centers in these parts of the world, also Pacific Islands, we can include them, and what, like the latest trends with the use of geothermal energy, how likely it is to make it happen on a wider scale?
Yeah, the economics of geothermal is very fragmented and very localization specific. But in many locations, you will see geothermal can be the lowest source of non-variable renewable resource, much cheaper than nuclear. So in all locations where you have not too deep sources, and we know those tectonically active area, then geothermal will outcompete nuclear without any doubt. But there is very large spread of the LCOE of geothermal power.
So I can't help note that in your 25-year forward forecast for energy growth and how it will be broken down, that you almost exactly mirror the IEA idealized pathway for the distribution of different things. But you also acknowledged that wind costs had gone up and wind investments had gone down because of those costs, yet you saw it going up again in the next 3 years, and you didn't justify why. And you didn't acknowledge the fact that the pathway we're on has diverged massively based on investment and the actual cost of these renewable powers, and that actually oil, gas, and coal have gone up every year. They haven't gone down, as the IEA has suggested. And the IEA recently, like less than a month ago, finally acknowledged that the pathway we're on is not the pathway that they put out. And I'm just wondering why you haven't acknowledged that in your forecasts.
Yeah, IEA is using our data for almost everything they do. IEA is not doing forecasting, but we do forecasting. What IEA is doing, they are doing what they say is various projections, but they don't talk about what is the most likely. I think that IEA think that what is most likely is maybe lower than. They have two scenarios now: the STEPS and the CPS. And the CPS is absolutely impossible in our view because it's too high. It will not be possible to deliver energy at affordable prices in those scenarios. Yes, our most likely scenario is significantly lower than the lower of IEA's two scenarios now. It's more aligned with what you said, the announced pledges scenario, which they had last year, but they abandoned that scenario now. And I think that is an overreaction. I think that in reality, the economics of the new energy will win. And you will see when China peaks on fossil fuel in a couple of years, because they are so large on the demand, then the rest of the world will also peak.
No, thank you. Now, Alu is already after me on time, so we're going to hear more from you, Per Magnus, in the panel. So you can use the rest of your slide for when Gregor is moderating.
Yep.
So we have now the wonderful Samira, and she's a researcher at the University of Oxford, and maybe you could take a minute to introduce yourself as well.
A whole minute, okay. I'm Samira. I'll try to make up for time, or at least I have a lot of maps for you, so I hope that's good. There was also, on the slide, Rick and Rabah's name just disappeared magically. It wasn't me. Well, so I should preface this by saying I'm an economist, traditionally, but I got really interested in working in specifically Africa and the Middle East, and you get very quickly into the issue of that you cannot do many things because there's not much data to do many things. Then I got really into satellites because they allow us to look into places that for normally there is no data. Mining was a bit of a demand-driven accident because mines clearly have a very clear spatial footprint. That the skills I was using to do other things in the context of gathering data for economic development in slightly non-traditional ways happen to also be applicable to mining specifically for the explicit footprint mining normally has. So a lot of my work is really about questioning that little subsection that economic research tends to overlook, which is the descriptive statistic. So don't just ingest the data that is, but question the data that you're ingesting, because if you build models on data that's questionable, then at best your model is questionable. So that's kind of where I sit, depending on which meeting I am. If I sit with the AI people, I'm introduced as the economist. If I sit with the economist, I'm introduced as the satellite AI person, so I'm whatever you want me to be. So I will talk a little bit. I have some more maps, so I hope I don't bore you, but they're a little bit more animated, so I hope the coffee hasn't yet worn off, and if it has, then maybe you can come back to life. Okay, there's a big entry. I did not plan this. So this is work that has been going on for some time, also throughout other projects with the lovely Baptiste over here, who him and I spend many Tuesday mornings trying to make the best out of a shitty data landscape at best. For this work, to give it a little bit more from a pure data science drive to also embed it in the economic discussions, I pulled in Rick and Rabah and says, let's embed this nicely within some of the econ question, because ultimately data is a raw material, and then what you do with it makes a big story. So how do you go from ingredient to recipes effectively? The point. But today I will mostly talk about measurement issues in a way. So what is the problem? The problem is that especially in economics, the majority of studies rely on a very finite set of data sources. And I'm talking specifically about data sources that have geospatial identifiers. So I'm glad this paper was mentioned a few times, because this also relies on SNP. At some point it was called SNL, before it was ingested into SNP. Of course, we like geolocated anything because we can mix and match it with other things, such as conflict or climate. But very little people seem to have questioned the validity of that, and especially in a sector like mining, where there is known to be also artisanal activity and also illegal mining. That in itself should make everyone question the data. Any data should be questioned, but then it should especially be questioned. So the issue is that we really have, most of the literature hinges on a few finite set of data, and that data has not been questioned. And if that data is questioned, you will start to question all the results. So it's really something you should pay attention to. So let's talk about S&P. I don't know if there's someone from S&P. I don't think so. So S&P mostly relies on publicly reported information. And they compile it in a very nice data source. Of course, they also do cost curves and all other things, which I don't do. So they are great for many things, but they should not be just taking at blind trust. You should check what is in it and what is not. Of course, it is also proprietary, so it's not open access, and it sits behind a paywall. What are the crucial issues? The crucial issues are when you evaluate it, there's generally quite large differences between what S&P reports as a sum and what the national statistics report. Baptiste knows all too well, because we had many headaches over this when trying to match S&P to BGS, for example. When you look at the spatial dimension, which is of course what I like mostly doing, is you see that mining locations that exist are generally not in S&P oftentimes, but also there's S&P reports there to be mines where there's none. There's indeed a forest without disturbance, which is a beautiful thing, and you don't see that often, but you wonder why S&P decide to put a mine there in their data set. And sometimes the points are just misaligned. So the point, there is a mine, there is a point, but the point is maybe 5 kilometers from the mine, which becomes an issue if you work on very spatially explicit problems. So there's all sorts of issues. And then as mentioned, because this is a sector with legal and artisanal activity and also corruption, that additionally is an issue. What is another issue is that S&P reports locations as points, so you actually don't get an idea of the physical extent of the mine, and you have, sand mines tend to be much more horizontal than coal mines, and you have no idea when just looking at S&P, except you enforce the hypothesis on output to floor space ratio, which of course is not true. So lots of things that are an issue. So some of them I already just talked about, so I can kindly actually skip this slide because I mentioned all of these things all together, and I will show you these also on a map so they become less abstract. I will skip to the dashboard in a second for sake of time. So here's a video. I hope I can make it play with this mount. No. Can you click? There's a play button. Is it playing? Yes. So you will face plant into the copper belt. I slowed this down, so hopefully no one is getting too dizzy. You can already see the copper belt here. This is way above flying height. You can see it already appearing there, obviously. I want to show you, take a little bit minds out of the abstraction into the real life, how big these things are and how do they look like. And then you realize with your eyes, you can clearly see that this is a mine. You can clearly see that this does not look like a forest. You can also see how close people live to the mine, which I think is quite important. Actually, there used to be a lot of buildings here, which were torn down without compensation to the people when this mine was expanded upon. But these are all the physical elements that I look at when I decide how to train a model. So what exactly am I looking at? Of course, there's like surface disturbance. There's disturbance from surface height, depth, and solely just color. And of course, this is tailings dam, so this is water. No, I have to skip to the next slide. This one. Out of the video back to a slide. So we now have traditional data issues, but we have all sorts of new options at our hands if we know how to use them that help us solve our problems, or at least in part. And I'm talking specifically about remote sensing, so satellites in combination with artificial intelligence. What artificial intelligence can do for us is it can detect mines at scale and at speed that we cannot do with our own eyes. We could just there's a lot of remote sensing without AI, and you can just look at satellite photos and with your eyes look for mines, but you just can't do that at speed, at scale, so you would spend a lot of time doing that. You generally still have to do that in order to generate a training sample. So you can take things from simple to quite complex. So an NDVI over there, so this is all a mine. This is, by the way, a mine that is not an S&P. This is what we call, it's simply a greenness index, no artificial intelligence included. It just tells you about how green a pixel is on this planet. And obviously you have seen mines are not very green. And if a mine happens to be in an area that used to be forested, you see a clear discontinuous change in the greenness. This is a road here, by the way. So you also see the roads, which are, of course, great indicators for mining as well. Then you have here near real-time land use modeling. So it's a model that has, so it's a classifier. So every pixel on the planet gets identified a land use class. So built up, forest, shrubland, etc. Mining isn't a class for itself, but you can see it goes under some industrial classifier. The beauty with this specific model is that you can use it in near real time. So the model has been trained once, satellite imagery comes available every day. This is trained on Sentinel-2, which is European Space Agency, so it's free to use. And then you can use the model and apply it to new imagery to come up with a likelihood of land use class. And then something that is very recent are geospatial foundation models. They basically are multi-instrument, multi-satellite compressed pixel values. So you don't have to start from zero, which what we had to have to do. We had to do a lot of work on the pure color bands of satellites, which is a lot of work and very data intensive. Now we have a bunch of foundation models, and these have come out in the last 3 months. So this is very recent developments. Developed by all the big ones. So the most common one here that's developed by Google and DeepMind. We have one that came out of Cambridge, which is also great because we like academic players in the field. We don't want to leave everything to the private sector. I do have to say this is an open model. So at least that's, and it's only been built on NASA and ESA data. So you can use these. They're not supposed to be finite models, but they're great for what we call clustering, so finding pixels that exhibit similarity in values. The values you don't identify, but if you know one pixel is a mine and you find something with similar values, then at some point you can assume it must be similar. So, it doesn't work anymore. Oh, it works, okay. Okay, I was just too fast. So how do I build a workflow? So I go from data that I know that exists. So this would be S&P. So I don't discard S&P fully. I just have a quality check and use it to find new mines. And I combine it with things from OpenStreetMap, because some mines are in OpenStreetMap that are not in S&P, which is weird because S&P could just ingest them quite easily. And then I went through the academic literature and looked for some colleague who had done similar work a few years ago. That was all before geospatial foundation models. So now we can even do the work that we could only do a couple of years ago. We can now do it much more efficiently and much quicker. And then I combine a lot of different layers of EO, so that's Earth observation. That's what we call satellite data. And I use a set of different algorithms. So classification is, so land use model is a classification. It's a yes or no, for example. Is it a mine? Yes or no? Is this a forest? Yes or no? Clustering tells you about something about similarity. And segmentation is what you use to delineate. So where does the mine stop? Because you want the extent. So I use those together with that input data, with some quality check, and I come up with a prediction of sites that could be potential mining sites. I'm very cautious in framing this because, of course, an algorithm can also make mistakes, so you want to do some check after the fact. So you come up with sites that look like physically could be mining sites, and I put you some examples there. And then I match them with data from USGS and the S&P locations that I have to say what is the likely material that's being mined here, right? So it's by proximity. And then I have a set of potential mining sites with potential mined minerals at those sites. Now, where do I find missing locations? Almost everywhere on the planet. This is relative. I excluded Antarctica because Antarctica always takes so much space of a map. So you almost find them anywhere on the planet, in some places more than in others. Some has to do with S&P displacement. So not every mine that's not recorded doesn't mean it's illegal. Something really has to do with S&P not being quite accurate with their spatial information. But this is really a global problem. This is not a local problem. And in some places, of course, more than in others. Now, I picked 2 regions here to show you the top 15 by total amount of mines, and then put the relative amount of mines that are known and unknown on here. And you see there's a lot of unknown mines in Brazil. You also see there's a lot of unknown mines in South Africa. So this is the top 15 countries in South America on one side and Africa on the other by the amount of mines that are recorded and not recorded. So you see it's really a big global problem, and if we don't get this right, then all the studies that rely on data that I mentioned before should also be equally questioned because the results shouldn't replicate the same way if you include all the mines. Now, I want to say the mines that are not recorded tend to be a lot smaller. You see here the mean of the not recorded mine tends to be 2 square kilometers in physical extent. Those that are recorded tend to be substantially larger. But there's also one suspicious outlier. I will show you the suspicious outlier in a second. Now, I got confused. I was like, this is way too big to be undetected. And then I found it, and then I found this article. That's exactly the mine that is there, and I will show you in a second. This is a huge gold mine in Peru. It's illegal, but it is very visible. Now I go to the dashboard, so I can actually show you something. So hopefully this opens in a separate browser tab. Otherwise, I might need the nice ladies to help me. Can you open this? Yes. So something should open. So I have to. Do you see a? No, it doesn't open. Okay, they're trying to fix it. So I can show you something on how this actually looks. Let's see. It worked before, so I hope it works again. Let's see. I don't know. They're doing something. It worked before. I saw it there, so it should be working. Oh, good. It's just a live map, so hopefully I don't have to do much talking. Is my timer paused until they fix it? Oh shit. Okay. Oh, there we go. Oh, it's coming. Good. You should have said that before. Maybe the map would have come faster. Fantastic. So I want to show you some things. I have to do it from this corner because I have to tap certain things. So where's the mouse? Oh, here we go. So I'm going to pull this map. I'm also not a Windows user, so I'm not used to a Windows computer. So I want to show you here. So we are now again in the Copper Belt because I mostly work in Africa and the Middle East. It's not moving. Oh no, it's frozen. What we can otherwise do is I let them fix it and I let Baptiste go first. No? Okay. Okay. The boss has spoken, so I will listen. Well, it's not, yeah, but that's not there. You're expected to see the places that are known, and then magically, all the places that are unknown, and you see there's a lot more on top of those that are known compared to those that are assumed to be known. So these are actually all the ones that are known, and then I would click something, and many more mines would pop up that are not in S&P. And then I wanted to show you some of the mines that exist in S&P, but actually when you check the location, there's no mine. And I wanted to show you the big missing gold mine in Peru. I do have to say, detecting a legal gold mine in Peru is a lot easier than in the Sahel because the gold mine is very yellow-ish, so as the Sahel, so it's a lot more tricky. But that doesn't mean you shouldn't do it. You should just be aware. Okay, we have now traveled. Let's see if I touch it. Do I have to? Can I just do it? Where is it?
It's another
Oh. But I need to, okay, I think we're running into technological issues here, but I'm very happy to show you on my computer if you want to see. So please ask. Oh, thank you. No, but I have to like click stuff and interact with it. It's technology. I leave you with that. I hope you get an understanding at least. I'll hand over to my amazing co-author, not on this paper, but on another, Baptiste.
Thank you. I don't know if you had questions or do you have them?
Maybe I'm going to pick on Timo if you paid attention. We have a guru in the room on big data. So any reaction? And anybody else? And then, okay.
So thanks, Samira. This is exciting stuff. So I guess this all begs the question, do you have any sense for us of how some of these key results in the literature might begin to change once you feed in the new, more accurate mining data?
Sorry, yeah. No.
Especially on the conflict one, I would expect that a lot of conflict locations were attached to mines, but actually also due to other mines. So I think in a way that should for sure change because the proximity, depending on how big you make the buffer, and I think in the big paper is 0.5 by 0.5 degrees, which is quite big. If you bring up all the small mines, then you actually see the mining activity should be much more intensive in places where there's conflict, but it wouldn't be attached to one mine, but it would be attached to the cluster of mines. And which, I'm not sure who of you is into organized crime, but there's a big push of informal gangs into mining to the point where it's outrunning cocaine in some regions of the world. And I'm talking that specifically Latin America. It's gold, but it's not just gold. So I think the whole dynamics about conflict of mine is changing, not just because we can measure it better, because that doesn't change the nature of the problem, it just changes the way we report it, but also the ownership is changing in a way that I think it will induce more conflict. But I know in the southern part of Nigeria, there's a criminal gang which has a truce with the local population because they take care of the environment better than the government does. So it's a very interesting conundrum there. But the estimates will change because I think in a way that we have a much more nuanced understanding of where conflict happens when. And obviously there's a lot of corporate interest to also reduce the reporting around all the issues around mining. So that mine that there was a mine in the Congo about 2 weeks ago that had a big collapse and 80 people died. That mine is not an S&P.
So I think with all of this, the ability to increase and shift the informational boundaries, as in like we get more and more visibility, you have the dual to that, which is obviously the escalation in outer space, which is to me sort of something that, I mean, I'm supposed to speak at some workshop on this. How do we think, for example, about, as we increase the transparency of supply chains, we might even encode that in our financial system through attaching metadata to payment transaction and so on and so forth. There's a fluffing of the boundaries between what is state informational layer, what's private informational layer, and what is a shared kind of common goal here, right? And so to me, I think your work clearly illustrates that because obviously the contest that we see happening around the extraction activity and the control of the resource rent maps on the other side in contesting outer space. And we have the same thing actually happening with ships. You know, the radar images for ships that are traveling outside of areas with the AIS signals turned off or turned on. We now have since 2021, we have a radar satellite, so a satellite that picks up AIS signals from the ungoverned seas that actually allows us to monitor that. And that's why we have the escalation, because there's some entities or individuals who believe that the resource rent should be private. And unfortunately, to me, this is institutionalized in the US. Of all the countries, it's most institutionalized in the US, because in the US you have a severance of mineral rights from surface and subsurface rights. And you have private ownership of mineral rights. Whereas like in most other countries, that would belong to the sovereign or the state, or the concept of the sovereign that is sort of in a state. And I think that is where Trump is not giving a very good impression of this in his sort of recent posturing around mining deals, because it highlights that sort of private interest around. Anyway, so it's just a meta comment on the bit, but your work illustrates this challenge that is sort of, yeah.
I can second that. Everything is political. So both AI and satellites. Obviously, satellites are deeply embedded in geospatial intelligence from the military apparatus, and wars have been fought and won over information advantage. And I'm just using it to make the world a bit more transparent. But both AI, I mean, Google scrapped their responsible AI guidelines last winter, so you can now use their algorithms for warfare, which I don't like war, so I'm not in favor. But yes, that is there. That's always, all the private sector satellite providers exist because of classified military contracts, not because of people like me. So it is true. You tread carefully, but you try to make all of these technology that we have useful for something that actually is good.
Thank you, Samira. Fantastic. Thank you, Samira. So we have two presenters now for the last paper before the lunch break, and I'm going to ask you to introduce yourself. Baptiste and
Ben. You can. Great. Thank you very much for this opportunity to present our work, and thank you to the organizers for everything before the workshop. It's been great. This is Benjamin Adams. I'm Baptiste Andrieu from the University of Cambridge, part of the Resource Efficiency Collective and funded by the Climate Compatible Growth Program. Unfortunately, we won't have any cool maps to show, unlike Samira, but basically Samira showed us that there were lots of issues with the quality of the data related to critical minerals, and we'll try to show that there are also issues on the ways critical minerals are identified and classified as critical or not. And Roderick summarized this as saying that basically it's useless to separate the two, and I think this summarizes our presentation. So I'll wait for this to come up.
But basically, raw material critical, okay, it's almost there. Criticality assessments tend to have 2 dimensions and be put in a, oops, sorry, it's still not there. Okay, great, thank you. So they tend to have 2 dimensions. One dimension being the likelihood of a supply disruption, here on the x-axis, and the other dimension being the vulnerability to such a supply disruption on the y-axis. And here there is a parallel between this and classical risk theory, where risk is calculated as the likelihood of an event multiplied by the consequences of this event. And so risk is the expected value of loss. Having this in mind, almost 10 years ago, 2 groups of researchers analyzed the field of criticality from the lens of risk theory. And their results were very harsh towards the field. Here are some of their points, but not all of them. So the first one is that all studies ignore the fact that there is a spectrum of severity of the events of interest. What this means is that many of the times there are lots of disruptions that could happen along the supply chain, and they tend to only focus on one, sometimes not even say which ones they're focused on, and not focused on the fact that there are different sizes of a given type of disruption. Second point is that many studies do not comply with the requirements set by risk theory, this being, for example, that you need to multiply both axes to calculate risk, and that this can lead to worse than useless outcomes. What this means, so if you remember the presentation from John Blundy, on the plot with the concentration, the distribution of critical minerals versus non-critical looked pretty random. And what this says is that sometimes you would get better results by taking a random distribution of your raw materials than actually following some of the criticality methods. And the last one is that almost nothing in these assessments are backed by empirical data, and it's almost always the subjective opinions of the authors. So these were really harsh almost 10 years ago. Since then, about 35 peer-reviewed papers have been published, and so we set out to systematically review every single raw material criticality assessments since 2017. And our results are unfortunately the fact that nothing has changed since then, and the same flows still occur. I'll give 2 examples of these. One of them is the way you distinguish between critical and non-critical metals. So on the left, it's an example from the literature, where here the raw materials are put in the matrix, and then you have these lines that say the further the line is from the origin, the more critical the metal is. So here, lithium is twice as critical as copper. However, the correct way to read this matrix should be here on the right, which we replotted with these lines that are multiplication of both axes. And here we see that all of these raw materials are actually supposed to have the same criticality level. Another example is the example from the European Union criticality assessment, where here they don't have these contour lines, but they just have thresholds, with anything above the thresholds of these 2 axes, here in red being critical and all the rest being non-critical. And then they also say, yes, but we know that copper and nickel are strategic raw materials and we'll add them to the critical minerals list. A few issues here. So we replotted this, and let's take the example of natural rubber that is here. When we plot the multiplication of both axes, we get this line, meaning that natural rubber is actually more critical than all of these yellow dots here, which are deemed not critical. And we could do it the other way around. Coking coal is actually less critical than all of these that are not critical. And then if we look at the copper dot, which is here, and the gray line, we plotted the gray line of the multiplication of both axes. And here, 89 of the 90 raw materials are actually more critical than copper. So here there's only 2 options. Either the probability of a supply disruption for copper is indeed close to 0, then copper is not critical, or the probability is not 0 and copper is critical, but then you have to change the methods. You cannot just change the results if the results don't suit you. Right, so this was for the peer-reviewed literature, and for this workshop, we tried to see if it was possible to review every country's list of critical minerals. The issue being that these lists can be published of course, in academic literature, but also just anywhere on the internet, be it on ministries' websites, on random consulting reports, or whatever. So try to set which countries have a list, how do they build that list, and what impacts this list has on policy. That's very broad, so we just have like an approximation of the results. And the challenge is, of course, that the lists are in different parts of the internet and in different languages. So to use this, we set out to use AI to help us on this. So writing very long prompts, explaining all of the project we were doing, that the results can be anywhere on the internet in any language. And then we tried lots of different models, every time feeding in a system prompt explaining everything we were doing, and then the specific name of a country for the model to go and explore the internet and come back with a list in the correct format and replies for each of these questions with URLs for each question in order for us to then check it manually and verify the results. So the preliminary results is that 86 regions have a list of raw materials that are critical, strategic. Of course, all countries don't use the same terms. 46 regions have some sort of methods explaining the list, even though these methods are not always clear. And 117 regions have some policies related to critical minerals. So more regions have policies than lists, meaning that critical minerals is now just in common language and people use it for lots of things. Here we identified 12 countries that have very detailed methods with PDFs explaining all of their assumptions. And this is 12 countries, and it's much more than the 5 or 6 that are usually taken as examples in most studies. Then we have 10 of them which have the overall method explained, but without the numerical details, for example. And we might have missed a lot, and we're still reviewing the results. And out of this, coming back to my previous point, only the list for the United States, made by the USGS, is consistent with risk theory, where they they built a whole really good model, but it's only for one type of disruption, which is trade bans in between countries. And this was published last August, and you could have a look. It's really interesting. So and then we tried, for every country, we had a list of up to 3 links with policies related to these lists. I won't delve too much into the details here, because first, we still need a bit of work on it. And second, I think most of you know much more about policies than we do. However, what's nice about these results is that they are a kind of a database where people can go have a look and say, oh, for this specific country, is there easily accessible policies? Right, and I'll now give the floor to Ben for the rest.
Thank you. Sure. Thank you, Baptiste. So essentially, just to conclude what Baptiste has presented so far, the methods for assessing which materials are critical are currently flawed globally, which means that the wrong materials are typically deemed critical. And we've just shown that they directly inform policy, and also the discussions that we have, for example, this one. So the question is, what do good methods actually look like? So we want them to be consistent with risk theory, as Baptiste presented. And there are essentially 2 ways of doing this. You can either do a simulation-based approach, which is what the United States have done, or you can do an indicator-based approach. And an indicator-based approach essentially means that you use metrics for things that you can measure as stand-ins for the likelihood and consequences of a certain disruption. So on the simulation-based approach, that's the gold standard, but it's highly limited in terms of data. So the USGS are the only country in the world that have actually done this, and they've only been able to do it for one disruption type, which is trade bans. That's because you need a detailed map of the entire supply chain across the world and a database of the historic disruptions to train your model against. So this is kind of our long-term strategy, what we're working towards. We've already made a little bit of progress on both of those points, but we are trying to be pragmatic about this to determine what are the immediate improvements that can be made to criticality assessments so that we don't continue to misprioritize policy levers. So this is our current priority, which is improving indicator-based criticality assessments. And I'll give you a couple of examples of where the existing criticality assessments fall short. when they're using indicator-based methods, just to illustrate the low-hanging fruit in terms of improvements that we can make even within the existing data that we already have. So the coloring on this slide's not great, so I'll just talk through it. But essentially, criticality or risk is likelihood times vulnerability. The way that existing assessments currently would compute this is to use indicators. And so we can consider two different disruptions, one which might have a zero likelihood but a very high consequence, and another which might have a guaranteed likelihood but zero consequence. So current approaches don't correctly treat these two cases as separate. So what they would do is essentially average the likelihoods and average the consequences to get a non-zero risk, when in reality they should be treated completely separately and then summed afterwards. So that's one flaw that existing methods use, which fills in the color afterwards. Sorry, I thought there was a color issue on the slide there. The second issue, which we can improve very easily within our data constraints, is around the way that risk is formulated. So similarly to bunching together different disruption types, a lot of existing methods bunch together different dimensions of risk. So typically risk is likelihood times vulnerability. But the problem is when you consider only two dimensions, that a lot of the indicators that would be used for vulnerability actually should not be summed in the way that they currently are, because they're causally sequential. So they should be multiplied together. So as an example, you could consider a chemical spill in a factory. You might have the likelihood of the chemical spill, the number of people in the way, and the proportion of the people that are not wearing protective equipment. So currently, most indicator-based assessments would put both of those latter two indicators as contributors to vulnerability, and they would simply add them together. Whereas clearly that doesn't reflect the causal chain of events. Really, these three factors should be multiplied. So that's another flaw that we've identified. And the number of dimensions that you should actually include in your risk calculation depends on the problem that you're approaching. So for supply disruption risk, we've come up with this formula, which is kind of import-dependent centric. So it's from the perspective of a country that has import dependence for critical materials. But essentially, we've developed an improved formula beyond what most of the current indicator-based assessments use, which is 4 dimensions, and it's a much truer reflection of the actual causal chain. And then the final thing is, of course, using the correct indicators when you're making these assessments. So as Baptiste mentioned, currently there's no empirical validation of the indicators that are used. So we're doing a lot of work to make sure that we're selecting the correct indicators and then assigning them to the correct dimensions within our risk framework. So essentially, I won't talk through these conclusions, but essentially what we've outlined here is that criticality assessments are important because they shape policy and they shape the discourse around criticality. And no one's really assessing which materials are critical in a very rigorous way. There are 2 paths that we can take. We can either take the simulation-based method, which is kind of a long-term view and requires a lot of data and a lot of computational analysis, or we can operate within our means and pick off these low-hanging fruits of ways to quickly improve existing criticality assessments using indicator-based methods. So thank you for your attention, and thanks to the hosts for having us.
Thank you very much. I think your question is central to this conference, and I would start by asking you whether on the risk part, you need to establish a typology of risk, right? How do you think about that? Because the area of risk that are involved in this concept of criticality is essentially infinite. So how do you go about the typology? Do you distinguish between downstream risk and upstream risk? Is there a standard there?
Yeah, thank you. Do you want to go on?
Yeah, I can take it. Yeah, so that's a great point. We kind of think about the core questions that we think about are really risk for whom. So which perspective is the risk taken from? and also what kind of risk are we considering. So I thought the point made earlier about engineers being more comfortable with multi-attribute measures characterized us quite well, because basically the approach that we tend to take is to assess risk from one perspective, and we assess it separately for economic risk, for human harm risk, for environmental risk, instead of trying to kind of unify this all into one. And those are the three dimensions that we use. So it's economic, human, and environmental. And we kind of try and map out the entire space using historical disruption databases to work out what the different causes of those risks are.
And we also have different types of hazards. And the ones that are, some of them have been really well studied in the literature, that is earthquakes and flooding, again by the people from USGS, where they take maps such as those that Samira showed us with all of the mines around the world. And then since it's earthquakes, we actually have probability distributions of earthquakes of different sizes. We have historical examples of earthquakes, so we can know what's the vulnerability to an earthquake, and then assess the expected value of loss due to earthquakes. And so I think we should have a different approach for natural hazards than for geopolitically induced hazards.
Of course, this leaves the weaponization aspect, but I think you were going to cover that. Oh, there were more.
Thank you. I completely agree with your analysis. I read also the paper from the EU and US Geological, and the definition of criticality, I agree, is very naive. I'm surprised that you have Denmark and Belgium and the EU. I don't understand. That means that why? How do you find this? Because I thought EU had the leadership on the definition of criticality for the EU member states.
Yes. So I think the EU states have to implement some of the things related to the EU list. But then on top of that, some countries can choose to have another assessment. And they actually use the same EU method, but just change the weights of import dependencies, for example, specifically for Belgium and for Denmark. And then I guess they can do whatever they like with this list, as long as it doesn't overlap with what's required by the EU.
Okay, and did you think about other approach for criticality, for instance, by looking at what we did in finance, like a stress test, like this? Like it looked like the simulation adopted, the simulation models adopted by the US, but the stress test allow you to. We used to do this in finance to see if a bank is systemic or not. So materials may be critical or not by. No.
Yes. So we haven't worked on this, and we started working on this only about 1 year ago. But in the literature, there is two very good papers. Unfortunately, I'm not sure I remember the authors right now, but that assess the portfolio risks of companies related to flooding. And so basically, they compare different companies with all of the distribution of mines in their portfolio, calculate the likelihood of floods, and then the amount. But I don't think this is exactly what you meant here, which I'll look into.
Two quick comments following this discussion, I think a very important discussion of what type of risk are we talking about. First, at least in the United States, it seems to me people are talking about two very different types of risk of disruption. There's a short-term disruption due to the geography of existing production, and this would be exemplified by focusing on import dependence and trade risk. That's a type of analysis that very quickly focuses on the lack of diversity geographically in production. That's very much the national defense discussion. On the other hand, the energy transition discussion applied to critical materials is much longer term in nature. The issue is the risk of lack of sufficient supply to meet the needs in 10, 20, 30 years for the new technologies, the wind, the solar, and so on. So the lack of capacity 10 or 20 years from now will disrupt the ability to undertake an appropriate energy transition. And these are really very quite different types of risk. Almost all of the national assessments that you study focus on this short-term lack of diversity today in production, and in my view are not, which is not to diminish your work, but that's somewhat different than the energy transition discussion. Second point, some work a decade or so ago by Tom Gradle and his group at Yale focused on environmental risk and actually had a third dimension in a three-dimensional map of critical materials where you had supply risk, vulnerability, and then environmental implications on a third axis.
Yeah, I think I have two questions related to energy. When you look at the probability and the consequence, I guess that the demand side is always on the consequence side. But how do you relate to whether you have a high demand for critical mining? I mean, a scenario, an energy transition scenario that goes very fast, like I said. We will be between 1.8 and 2.2. That is what we think we will be in global warming. How does this impact your criticality measure? And one more question. So what induces most risk for critical minerals from the three sectors, defense, IT, semiconductors, and energy? When you are playing this risk methodology? Second question.
Thank you very much. I will be very quick. As you mentioned that you used Gidel's data, I worked with this data. They're very messy, so there's a huge work of cleaning the data. And something that could be interesting to explore, I guess, but difficult to model the risk distribution is the concept of geopolitically critical. Because if you, what you mentioned about the distribution of the earthquakes and the consequences that you can model quite nicely, the type of criticality, it is going to a direction that what has been mentioned, and conditional to a huge data cleaning, you can identify somehow in the Gidel data, this kind of disruption due to geopolitical reasons. Then the problem would be to postulate a distribution, because we don't know when Xi Jinping decide to make an export ban, when Donald Trump decide to make, so interesting but difficult to model.
Global events are governed by the actions of people who we can't predict. And if that's the answer, well then we throw out the rule book basically. But we've kind of got to do the best we can with the data. To your questions, I think really those are great questions. They're largely to do with kind of the demand for critical material and how different demand scenarios and different industries play into this risk question. That's, to be honest, that's kind of outside the scope of what we've looked at so far. So really what we're looking at is how we can use the data that countries currently use in a better way. So essentially, a lot of the work that we've done so far, as Baptiste mentioned, we're quite new to the field, is essentially looking at, given the metrics that they're currently using to predict, can we determine which ones are relevant, and can we determine how they should be combined to arrive at a criticality score? So we don't actually look specifically at kind of separating out different industries of demand and things like that.
Great, thank you. I'll try to be very fast because I know we all want to go to lunch. Just very quickly on GDELs, the way we're thinking about it is having different archetypes of disruptions from these, building machine learning models to say the likelihood of disruptions, validate these on, especially for earthquakes and everything that we have other good databases for, and if we show that we can validate them on things for which we have other databases, then we might be able to trust it for things where we don't have data. On the future demand and these scenarios that Rod, you discussed, I think one interesting point there is that the people who are focusing on a long-term risk are people from industrial ecology, which unfortunately are very rarely geologists, and so they tend to have a very naive view of geology and have, for example, just take the reserves indicator saying the less reserves, the more likely there will be a future disruption, even though for 150 years we've had constant reserves of copper, for example. And so I think we need more geology in this and investment dynamics. And on your second point on the environmental dimensions, the way we think about this is that we should calculate risks in different units rather than adding dimensions, because the environmental damage is one way to calculate risk. The people who die from earthquakes or from mines collapsing is one way to calculate risks. And the economic loss for the countries is another way. And unless you say, this is the trade-off because I'm a policymaker, it doesn't really make sense to me to aggregate them in one single indicator.
For the lunch, Audrey-Anne and Bulbul will guide you to the place of lunch, the corridor. Thank you very much.